All right, so today's notes are on multiplying and dividing radicals. Our content objective is to do just that, as well as to rationalize radical expressions. And then our language objective is to use the correct terminology to describe radical expressions. The first key point I want to delve in with, which we've kind of implied in our process of simplification, but what this says is that if I'm multiplying two radical expressions that have the same index, so it's this index, or the nth root of a times the nth root of b, and we're talking only real numbers, not imaginary and complex, then I can put them under the same radical. So if I multiply the nth root of a times the nth root of b, I can rewrite that as the nth root of a times b, or I could go the other way. So I can switch between these two forms as long as these have the same index. So just to make sure that makes sense, I want you to try some quick checks real quick. Pause it if you need to, try them out. I'm going to go over it now. The first one, hopefully you can see this. I have the cube root times the square root. And we can't simplify this because they have unlike indexes. So the indexes are not the same, so I cannot simplify them using the rule that we just talked about. The next one, however, I have the cube root of -4 times the cube root of 2. I can rewrite that as the cube root of -8 because that is -4 times 2. This would be the cube root of -4 times 2, which becomes the cube root of -8, which is just -2. So I could simplify that second one to -2 because those have the same index. I can multiply. So the last one, I threw in some variables to make it a little bit trickier. So I again have the same index. I'm taking the cube root of each of these. So I end up with 9 times 3 is 27. X squared times x is x cubed. And then I have a y. So since I'm taking the cube root, I know the cube root of 27 is 3. The cube root of x cubed is x. And I'm left with the cube root of y still there under the radical. So again, I'm doing some shortcuts. I recognize some perfect cubes in here. If you prefer the process of simplification where you make your prime factor tree, that works just as well. I'm just doing this for the sake of time. So as long as you end up with these final answers, you should be all set. So the next key point is similar. So it just says that if we have, again, two radicals with the same index and they're being divided, I can write them under the same radical. So the same way you can write them under the same radical if they're multiplied, you can write them under the same root if they're being divided. So I'm going to have us jump right in and try simplifying a couple of these. So if you can pause, do a quick check. I'm going to go over it. Okay, so the first one, I'm going to rewrite this as the one under one radical. So I have the square root of 18x to the 5th over 2x cubed. 18 divided by 2 is going to be 9. X to the 5th divided by x to the 3rd is x squared. So again, since I'm dividing, I subtract their exponents. One of the reasons we spent some time practicing all of our exponent rules. So the square root of 9x squared is just going to be 3x. So the square root of 9x squared is just 3x. So that is my answer for that one. The next one, again, I'm going to do the same thing. I'm going to put them under the same cube root. So when I put them under the same cube root, I get 162y to the 5th over 3y cubed. 162 divided by 3 gives me 54. Y to the 5th divided by y to the 3rd gives me y squared. So again, at this point, you can do your prime factor tree and do that out. I'm going to do my the other method where I rewrite this as 27 times 2, because I know 27 is a perfect cubed, times y squared. I cannot take out the 2 or the y squared since they're not perfect cubes, but I can take out the 27 and write 3 times the cube root of 2y squared, and that is my final answer for that one. All right, so that's multiplying and dividing radicals. So it's mostly just the simplification process that we've been practicing in class, with the added step of either multiplying or dividing beforehand. So pretty much the same thing, slightly one added step. But the other thing I want to go over that's a little bit trickier and a little bit different from what we've been doing in our last lesson is rationalizing the denominator. So rationalizing the denominator means getting radicals out of the denominator. So mathematically, normally we don't leave irrational numbers in the denominator. So we're going to practice getting them out of that denominator. So our first example, I want us to write the cube root of 5x squared over 12y squared z in simplest form. So the first step to rationalizing this denominator is separating the numerator from the denominator and writing these as two separate roots. So in our last examples, we practiced going from this or from 2 to 1 root. Now we're going to take this from 1 root into 2. So I'm going to rewrite this as 5x or the cube root of 5x squared over the cube root of 12y squared z. The next part is what I think is a little bit tricky for people. So because I'm taking the cube root, I'm going to figure out the values I would need to multiply this denominator by to make each part a perfect cube, or to make 3 of a kind for each of these things. So if I'm looking here, I have 1 12. I need 3 12s in order to take it out because I'm taking the cube root. So I'm going to write 12 squared here because I need at least 2 more 12s to make that 3 of a kind. Y, I have 2 y's, so I need to put only 1 in there to make 3 of a kind. So I already have 2 y's, so I find my third. Z, I only have 1, so I need 2 of a kind. So I determined what values would make perfect cubes, or 3 of a kind in the denominator, since it's a cube root that we're finding. If I were doing a square root, I would only need 2 of a kind. If I were doing a fourth root, I would need 4 of a kind. But ultimately, my goal is to get the number of, or get perfect cubes or perfect terms to the fourth power, perfect squares, and under a radical, so that I can ultimately cancel it out. And you'll see what I mean in just a second. So I can't ever just multiply one part of a fraction by a value. So when I find this, I have to multiply both the numerator and the denominator by this cube root that helps me make the bottom a perfect cube. So my goal is to make the denominator a perfect cube, and then I have to multiply the numerator by that same value so that I'm not changing the value of my original fraction, I'm just simplifying it or making my denominator a perfect cube. So when I multiply that out, I end up with the cube root of 5 times 12 squared is 144, x squared, so I'm just put my numbers next to each other. So I did 5 times 12 squared, 5 times 144, x squared, there's no other x's, y, z squared. So that's my new numerator, and that's, so now I'm multiplying these. I'm on step 3 if you're trying to follow along. And in the denominator, just so you're clear on what happened, I now have the cube root of 12 cubed, because I had 12 times 12 squared, which is 12 cubed, y squared times y, which is also 12 cubed, and z times z squared, which is again z cubed. So now I've multiplied these all out, I can start my simplification process. So here, my numerator, if you wanted to do, I can do a factor tree for you. So I'm going to simplify my numerator first. So I'm going to bring this over here. I have 5 times 144. My x, y, and z, none of them are perfect cubes, so I don't need to simplify that out. So 144 is 12 times 12, which becomes 4 times 3 and 4 times 3, 2, 2, 2, 2. So my prime factorization would be 5 times 3 times 3 times 2 times 2 times 2 times 2. So I have 1, 2, 3, 4 2's, 2 3's, and a 5. I'm doing a cube root, so I'm only taking out 3 of a kind, so I'm taking out my 3 2's. So when I keep simplifying, I have 2 cube root of 5 times 3 is 15, times 3 is 45, times 2 is 90. And then my x squared, y, z squared, none of that changed. So I simplified the numerator. Now I have the denominator. And so these are all perfect cubes already. So all I have to do is cube root each of these. So for this part, all I do is cube root each part. I have 12yz because I purposely aligned it that way so I can do that. So my last step is to simplify this. So 2 and 12, I can simplify those. So that becomes just the cube root of 90x squared yz squared all over 6yz. So 6y, this is our final answer. And we are all done. So I know that's kind of a lengthy process. I'll do just a couple quick checks to see if it makes sense to you. I just want you again to simplify. And I'll make these a lot smaller than the other one. So I have the square root of 2x over 3 as our first one, and we'll do another cube root of 5x over 2x squared as the next one. So try those out real quick. I'm going to go over them now. So this is a square root. I only need a pair to get rid of it. So I'm going to multiply by the square root of 3 over the square root of 3 because I just need to get rid of that 1, 3 under the square root. I end up with the square root of 6x over the square root of 3 squared, which is just 3. So again, I'll show the in-between step. I had 2x times 3 over the square root of 3 squared, which brought me to that value. So this one, again, I need to multiply to get 3 of a kind. So I need to do 2 squared and an x cube rooted. So I need the cube root of 2 squared over, or 2 squared x. When I simplify that, I get the cube root. 5 times 2 squared is 4, so it's going to be 20x squared over, and this is 2 cubed x cubed, so it's just 2x. So again, if you wanted the in-between step, I had 5 times 2 squared times x cube rooted over the cube root of 2 cubed over x, 2 cubed x cubed, which became this. All right, we'll practice that some more in class, but make sure you write down any questions, comments, or concerns so we can go over them together then.